All right. So hello everyone. My name is Hao Wen, and I'm from NebulaGraph, and our company is called dissect. And let me introduce a little bit about our company. So our company was founded in 2018, and our founders are from like Meta, Alibaba, and Accenture. And our vision is to become the number one graph database in the world. And currently, we are ranking number 2 on DBMS on DB engine in terms of the graph database, native graph database. And here's a little bit introduction about the features of NebulaGraph database. So first of all, we are targeting large scale and high performance scenarios. And we support super large scale data set. So the maximum data set that we see on our customers are 100 billion vertices, 1 trillion edges, and 200 terabytes of data in terms of the data size. And we are standard leaders, and we are among one of the first vendors who implement the ISO GCO standard. And the ISO GCO standard is the second ISO standard in the database area. And the first one is ISO GCO, which was already 40 years ago. And ISO GCO standard was released April last year. And we also support MCP. And the performance is our confident. It's what we are confident about. So we support very high QPS, like 1 billion, and tail latency is very low, 3%. And we also provide open source version that you can try out. Okay, so today I'm gonna maybe talk about our new product called our GraphRAG, or our AI platform based on GraphRAG. I will introduce a little bit about like why GraphRAG and not VectorRAG, and what we invented in this GraphRAG field. So first of all, the question that many enterprises will have when trying to apply the large language model is how to use the large language model. So here are several methods. The first method is fine tuning. Okay, so this is kind of extreme. People will retrain their model based on their internal private knowledge, and then they will be able, the retrained model will be able to answer the questions based on their internal knowledge. But the issue is this is very expensive, not suitable for all companies, and it's also it also requires to retrain every time you update your documents. Okay, and the other extreme is prompt engineer. It's basically don't do any retrain, but directly tweak your prompts to try to get answer from the LLM. But the issue is with prompt engineer, the large language model doesn't have access to internal knowledge, so it cannot solve the hallucination issues. So between these, we usually recommend using RAG, because it's cheap, right? You don't need to retrain any model, and it has access to your internal private knowledge. And this is the paradigm of the RAG. So usually it will create an index of your internal knowledge, and during the query process, it will retrieve the knowledge from your database, and then send the retrieved knowledge to the LLM to generate the final answers. When people talk about RAG, people usually talk about the vector database. Okay, but we find actually there are several issues or challenges of the traditional vector database. The first one is the vector database is hard to differentiate fine-grained factual difference. For example, here I have 2 questions. One question is, what's the GDP of the United States in 2024? And the second question is, what is the GDP of the United States in 2023? these two sentences only differs in 1 digit, but in vector space, they are very similar. And the second issue of vector RAG is lacking of contextual and multi-hop connections. So vector RAG is not good at a question like, what's the relationship between these two documents, right? And the third issue is the vector RAG approach is heavily depends on the similarity comparison, but mathematical similarity doesn't equal to semantic relevance. I will provide an example of this later. And the last one is vector RAG is very limited in answering those global search or reasoning intensive questions. For example, a question like, how do you like all the materials that are uploaded? What are top 5 important points that you can summarize from the documents that I just uploaded? So these kind of questions is not some like the traditional vector RAG is good at. So since pure vector-based RAG has these limitations, what else can we do? So an alternative is GraphRAG. So on the left side is the paper published by Microsoft Research last year. And actually, our NebulaGraph proposed this idea actually even earlier than Microsoft. And they cited our work inside their paper. I will walk through the limitations of the vector RAG and discuss how GraphRAG can address this. So the first one is the chunking selection. So the very first step of creating an index in vector database is to slice the document into chunks. Then the first question that you need to answer is, what's the chunk size? The size of the chunk affects the quality of the text segmentation. If the chunk size is too small, just like the example over here, at the top, you may cut the sentence into very small fragmentations, and this may not represent the real meaning of the original sentence, and you may even end up with an opposite meaning of the original sentence. And if the chunk is too large, just like the example over here, okay, it's almost the whole paragraph, then the real information will be buried. For example, I'm trying to ask a question, and the answer matching this question is just a few words in a large chunk. Then the similarity that you get between my question and this large chunk is very small. So the optimal chunk size for different types of text is unpredictable and may not even exist. And the next issue that I've already mentioned is the vector relevance doesn't mean semantic relevance. So let's take a look at an example over here. So here I have 2 sentences. The first sentence is apple is valuable because it provides the vitamins that people need. And human being can easily tell this apple means a fruit. And the second question is apple is valuable because it provides intelligent experience that people need. After some thinking, people can also easily guess, have a high confidence guess. This apple means Apple company or products from Apple, right? But if we transfer these 2 sentences into vectors, you will end up the embeddings like this. I'm just here to provide an illustration. The actual dimension of the embedding will be much larger than this, but you can see in terms of the vector, these 2 sentences will be very similar. And another example is the 2 graphs over here, like coral and Korea. These 2 words are representing exactly totally 2 different things, but in terms of vector space, they are similar. And the third challenge is the contextual linkage and multi-document relationship that I mentioned that earlier, that the vector RAG is not good at to preserve the relationship between documents. So assuming I have a a multi-level or hierarchical document like here. So this is the level 1 department document, and these are the level 2 department documents, and these are the level 3 department documents, and they will reference to each other. Like a level 2 department document will reference some contents in the level 1 department document. Okay, so if I use vector database to store them, I will just slice the document into chunks. And these chunks in different departments are just equal. They are just chunks. They don't preserve any information like whether it's from like level 1 or level 2, or it doesn't preserve the citation information, or it doesn't preserve any reference information. They are just equal chunks. Okay, but if we use a graph database, we can create a graph like this. For example, I will create, first of all, I will create a node called L1 department, and also a node called L2 department, and a node called L3 department. And then I will create all the nodes for, I will create a node for each document and create a link or edge called publish to link the department and the documents published by this department. Okay, so I will create three groups: the documents of department 1, documents of department 2, and documents of department 3. And let's say this document C published by L2 share some common entities with this document D from department 1. Then I can create an edge like this, saying that these two documents are related because they share the same entity. Okay, so by this means, I can create a relationship between different documents very easily. It's very natural. So what's the impact of the difference? So the impact lies in this global search and community level reasoning. So assuming on the right side, assuming we have 3 different type of questions. Okay, so the first question is, what is the main content of the doc from the level 1 department? This question is very direct. It's just a single question, a very simple question. And if we use a vector database, it can answer this question pretty well. Okay, because it just need to find the chunks related to this document. And what if I have this question, like what is the relationship between doc A from level 1 department and doc C from level 2 department? It can find the documents, the related chunks of level 1 department and the related chunks of doc C from level 2 department, but it cannot find the relationship because it's just not there. It's not stored in the vector database. And how about the third question, like what are the top 5 important messages? And it's really hard because the vector database doesn't know how to do this. Then what if we have a graph database, right? We have a GraphRAG. For this question number 2, like what's the relationship between doc A from level 1 department and doc C from level 2 department? It can easily achieve this search first by locating these 2 documents, right? This document and this document. Then by applying some like a subgraph match or some very mature established graph algorithm, it can easily find the connections between these 2 nodes by exploring this graph. Okay, and how about this question? Like, what are the top 5 important messages? This question also be answered easily by applying some graph algorithm like latent community detection to divide the graph into several communities, and then summarize of each community, and then answer based on the summaries. But is this GraphRAG enough? No, the GraphRAG still also have some issues. Comparing with VectorRAG, the index stage of GraphRAG is more expensive and takes more time. And it's also not good at multimodal contents. Like vector actually can transform everything on the world into embeddings, but not all data can be transformed into graph. And also, GraphRAG has issues of inconsistent data sources. Also have issues when there are inconsistent data sources. For example, when answering a global or multiple question, GraphRAG may unintentionally merge information from two different document versions. For example, I'm trying to ask a question about Apple.com financial status analysis, right? Then I can got two different analysis reports from two different companies. They may have conflicting results or conflicting information. Then by using GraphRAG, the general answer may combine these conflicting numbers from both of the documents and then send you the result and generate and send the results to human beings. This is something that is very hard for GraphRAG to avoid. So that's why we introduced this concept of called Fusion Graph. This is our invention by NebulaGraph. So Fusion Graph leverages the document metadata and hierarchical structures. So our base layer of our foundation is still knowledge graph, but we build another layer to index document level metadata and document structure like sections, chapters, and chunks. And with this Fusion Graph, our indexing can be faster than our own version of GraphRAG, like five times faster. And our own version of GraphRAG is already 20 times faster than the Microsoft GraphRAG in terms of the index building stage. And we are also more accurate in question answering. And our GraphRAG, Fusion GraphRAG, is built upon our underlying NebulaGraph database, which supports not only graph index, but also supports vector index and full text index. So we have the capability to utilize all the advantage of these three indexes, vector index and full text index and the graph index, to generate the results, to generate the best result. And we also enhance those multiple graph algorithms to help the search, to help the retrieval of knowledge. So I've mentioned that this Fusion Graph is kind of our invention, and upon that, we built our Nebula AI application SDK for developers to call the functions of our Fusion Graph. And we also have a Nebula AI application platform, which is an end-to-end product for user to use from OpenBox. And we also have a cloud service of this Nebula AI application platform. Yeah, I've already mentioned that the foundation of our GraphRAG product is NebulaGraph database. Then maybe I can introduce a little bit about our NebulaGraph database and see how it can and why it can support our GraphRAG product. Yes. First of all, our NebulaGraph database is a separated compute and storage architecture. And our compute node is called GraphD and storage node is StorageD. Since it's separated architecture rather than co-located architecture, we can achieve more flexibility and more elasticity, and we can have a better scalability. And this compute node and storage node can scale independently. And the storage node is using shell nothing structure, so it's easy to scale and also fault tolerant. And data are being partitioned into a lot of small partitions, and the partitions are way more than the number of partitions is way more than the number of storage nodes. And each partition is replicated into multiple replicas. And each replicated partition will be assigned to a storage node. When serving a query, the compute node will find the corresponding partitions, will find the partitions responsible for for achieving this query, and then access the corresponding storage node to retrieve the data. And we have a consensus layer built upon RAG consensus mechanism to ensure the strong consistency between replicas and high availability and high durability. And we have a centralized metadata service, which is also distributed to store the metadata information like schema, leader information, user information, and etc. And this is the architecture of our Fusion GraphRAG. So you can see NebulaGraph is sitting in the middle of the structure. So we allow users to upload all kinds of documents. So yes, our Fusion Graph, NebulaGraph is multimodal. So we support not only documents, but also image, tables, and all kinds of documents. And based on the index that people want to create, right? So we create with NebulaGraph support vector index, full text index, and graph index. So based on the index that people choose, we can create a graph or embeddings. And then we'll store either graph or embeddings inside NebulaGraph. And when people ask a question, we will either create an embedding of the question or split the question into multiple nodes. And then we will create a query plan to answer this question. And this query plan is mainly about how to search the vector database and how to search the NebulaGraph using vector and how to search NebulaGraph using a graph index. And then we'll retrieve the data being stored in the NebulaGraph database and send to LLM to generate the answers. Yeah. And this is the overview of our NebulaGraph application platform. So this is the interface, and you can see you can create an app on this interface. So it requires 0 code to build AI application, and inside each app you can reference which documents or which knowledge set that you want to use to answer this question. And we also have an interface to show the indexes, right? So here is a visualized graph index, and with this visualized index is explainable and auditable. You can tell why the answers is generated like this. And this is the interface of the question answering. It's similar to ChatGPT. So you can use natural language to ask questions. And our question answering accuracy is high. As of October 1st, our question answering accuracy, it can reach 0.81 on benchmark data set. And the question is not a naive question, it's complicated multiple question when we evaluate this. And even some customer data set, we can reach 95% accuracy. It's better than the best open source solution, which can only achieve 0.71 accuracy.